Modern sequence modeling now handles datasets ranging from thousand-page documents to high-resolution video, but these massive inputs push current hardware to its processing limits. The standard self-attention mechanism works by projecting an input sequence into three distinct representations: queries, keys, and values. The computational bottleneck occurs when the model calculates the product of the queries and the keys. This specific operation creates an n-by-n attention score matrix. This n-by-n matrix scales quadratically. If the sequence length doubles, the required memory quadruples. A 100,000 token sequence requires a 10 billion entry matrix per attention head. This requirement instantly exceeds the capacity of current enterprise GPUs. Even during the decoding phase, the model must maintain a key value cache of all previous tokens. This cache grows linearly until it hits a hard memory limit. This quadratic scaling acts as a rigid physical barrier, preventing models from natively understanding massive datasets, like whole genome sequences. To bypass the O(n)² wall, researchers developed a method to skip unnecessary calculations: sparse attention and binary mask. This binary mask restricts the query key pairs that interact, effectively zeroing out the majority of the grid. The algorithm computes the product of the queries and keys only for those specific active entries. Next, the model aggregates the values based only on those remaining sparse attention weights. By ignoring indices where the mask is 0, required dot products drop from n² to only the number of non-zero entries. Mathematically, removing 90% of these operations should result in massive speedups. But on actual GPUs, this theoretical efficiency often fails to deliver faster runtimes. Once the majority of connections are masked, the model must use a specific geometry to decide which tokens are allowed to interact. One common pattern is sliding window attention. Here, each token attends only to its immediate neighbors to capture local context. Strided attention expands this by having tokens skip at regular intervals, capturing longer range dependencies without increasing compute density. Global attention designates hub tokens to attend to every other token, ensuring information flow across the length. Random attention adds stochastic connections, allowing information to jump across the sequence. The Big Bird architecture combines these local, global, and random patterns into a single mask. Because this combination ensures that any two tokens can communicate through a few intermediate steps, Big Bird maintains the property of a universal approximator. It can theoretically match the capabilities of a dense transformer. Other architectures, like the reformer, use locality-sensitive hashing to dynamically group similar vectors into buckets rather than using a fixed pattern. While these complex topologies solve the O(n)² barrier on paper, their irregular shapes create a significant mismatch with how hardware actually retrieves data. Theoretical efficiency is often an illusion because it ignores the physical architecture of the GPU. Modern GPUs use a memory hierarchy. High bandwidth memory, or HBM, provides massive capacity but slow transfer speeds. Static random access memory is extremely fast but has very small capacity. Standard attention is memory-bound. Time is spent moving data between HBM and SRAM, not performing math. Unstructured sparse attention forces the GPU to search for scattered metadata across the HBM to find which query key pairs are active. These scattered, unorganized data requests fail to stream efficiently. The resulting congestion starves the compute cores and slows the entire system. This leads to uncoalesced reads, where memory bus utilization drops significantly. A 90% reduction in math operations is irrelevant if the memory bus is too congested to feed the processor. Real speedups require hardware-aware algorithms designed specifically for the way GPUs move data blocks. Block-structured sparsity solves this by grouping active data into contiguous 16 by 16 blocks. These contiguous blocks allow tensor cores to operate at peak efficiency on the active chunks, while simply ignoring the empty space. Alternatively, flash attention computes the full dense matrix but optimizes the memory access pattern itself. Flash attention uses a tiling mechanism to load small chunks of data into the SRAM, compute them, and write the final output without ever storing the massive intermediate matrix in the HBM. Newer versions, like Flash Attention 3, use specialized hardware instructions on NVIDIA Hopper GPUs to further increase this efficiency. For short and medium-length sequences, these I/O-aware dense mechanisms frequently outperform the sparse algorithms that were designed to replace them. Because transformers must cache all previous context, they eventually hit physical limits in memory bandwidth, regardless of optimization. State space models, like Mamba, offer a different approach by replacing context caching with context compression. While a transformer's cache grows linearly with sequence length, a state space model compresses history into a fixed-size state that remains constant. This compression is lossy, meaning these models struggle with exact verbatim retrieval compared to the perfect recall of dense attention. The most effective current models are often hybrids, using state space layers for global context and local dense attention for specific details. The pursuit of infinite sequence modeling has shifted from simply reducing raw math to a reimagining of how systems distill and retain information.